Hello and welcome to the next video. In 8.5, we're talking about not only recognizing but dealing with complex numbers. All right, what is a complex number? A complex number has two parts to it. It is both real and imaginary. It's very similar to a binomial. If I had 2x plus 3, this is a binomial. We cannot simplify it anymore as they are unlike terms. They have two terms. They are not alike each other, right? And we've done multiple things with this. We've added them to other things. We've subtracted them. We've multiplied, divide. We've factored. We've composed. We've done lots of operations with these binomial things and trinomials and all that jazz. Complex numbers operate the same way. What you have here is two parts to this one number, one being real, a whole three, a three that operates alone, and an imaginary part. Now remember, there's only one true imaginary number, I, but we're going to rope 4i as the imaginary part of this complex number, okay? Here in 47, we have a real number here in 47, and then the minus 25 is the imaginary part. You could do this with anything. You could have the fraction version here. We've got fractions and rationals right here, imaginary. You could have trig values. You've got real and imaginary, right? And that first real number is crazy looking. The cosine of 2 pi, right? That is not something that is on our number line often. It's definitely a non-terminating decimal, but it's still real. I could add it to my number line if I felt so inclined. What I can't add to my number line is 3 pi I. There's no 3 pi I on the number line. So don't be confused. It's not the complicated part and the real part. It's the real and imaginary part. It's the part with the I and the part without the I, okay? In general, we can see it as A plus B times I. So A is the real, B is the not real. Cool. Let's start adding and subtracting, multiplying, and dividing. Again, these operate the exact same way that binomials do. So we're actually going to go through this a little quickly. Here we go. We're going to start with the first complex number plus the second complex number. I'm looking at this as combining like terms. The like terms being the real parts and the like terms being the imaginary parts. Luckily, I has been taken care of as a separate, almost a variable type of thing, and so I can just combine those coefficients as if it was a real number. I can do the same move as if it didn't break any laws. All right, let's do it again. I got three things adding here. I'll combine all these parts. 7 minus 6 is 1. I'll combine the imaginary parts. What's convenient about real numbers is we tend to write them in the same order, and so they're usually easier to find than binomial problems. Let's see, 2 minus 1i would be 1i, plus 3i is 4i. And that would be my new complex number. Notice how in both cases, I end up with another complex number, okay? This is not going to be a case where you're not going to end up with a real and an I. There might be some cases where you end up with like a weird looking one, but you're not going to suddenly have three terms, okay? Same thing goes for subtraction. You just go real by real. Let's see, 3. Now on subtraction, again, we have to be careful. If you would like to change the second complex number to minus 3 minus 2i, then that's fine. You're applying an idea, but you're not actually subtracting that number, okay? You're just making sure you remember to subtract both of them. But in either case, we get 3i. 5i minus 2i is 3i. Let's do it again. We can apply that idea here since there's a lot going on. There's a subtraction and an addition. So maybe I'll just change that to minus and plus, right? Same routine. 8 minus 7 is negative 1. Plus 3 would be 4. So I did these three here, right? Because those are the real parts. In the other part, the imaginary parts, minus 3i plus 6i minus 2i. Well, remember, addition is commutative, so maybe I'll do the minus 3 and the minus 2 first, which would be minus 5. Add that to 6, you get 1. So plus I. If a color scheme helps you as well, then feel free to use it. All right, the last thing you're going to see is sometimes when you add them, something drops away. So in this next one, when you add it, 9 plus negative 9 is actually going to give me 0. So my real part has dropped away. But the other part, the imaginary part, I do still get a 12i out of it. You can write it as a complex number like this, but just like when this happens in binomial, feel free to consider it a canceled out situation and just write it as 12i. Also happens the other way around. If I had 4 plus 2i and 6 minus 2i, well, then these two would, I'm sorry, plus in the middle. Let me rewrite that. Sorry, there should be a plus sign in the middle. 6 minus 2i. Well, then feel free to consider these two canceling out, and we're going back to a whole real 10. It happens. It doesn't really change or break any laws. It's just something that can happen, so watch out for that. All right, that's adding and subtracting. Let's talk multiplication now. Again, multiplication, we can consider this a binomial, and so we can follow the same rules of binomials. Remember, multiplication of binomials comes down to distribution. You basically just distribute in both parts of the number. In this first one, we're talking about one imaginary number times a complex number. Totally legal because we're considering the I a variable idea, and so we'll just distribute. We get 8i plus 12. What do we get here, though? What happens when you times x to an x? You get x squared. And so here we will get I squared. Same laws being applied. Since it is an I, though, and not some random floating variable of unknown number, we know what I is. There's one more step we gotta do. Remember what I squared actually means? I squared ends up coming back and being a negative. So we have one additional simplification here. That 12 is now a negative 12. And normally we write them as real part first. So negative 12 plus 8i would be my final answer. So one additional step with these, you may want to put a star by it so you remember to do it. Just watch, make sure you save it for the end. Do all of your multiplication first and then simplify, just like normal, right? Consider it another combining or another simplify step. Let's do another one here. I'm going to use blue. This I can look at as binomial times a binomial, so I'm just going to do 3 times 4 and 3 times negative 2i. I'm going to do 5i times 4 and the 5i times the negative 2. So again, each paired up. I have 2 terms and 2 terms, so I get 4 combinations, right? Here is 12. The real parts I will multiply, so minus 6i. The real parts I will multiply, so 20i. And the real parts, pardon me about that, I'm at school recording video right now. This would be negative 10, and now I will also multiply the imaginary parts. I get I squared. Okay, let's do some combining now. I'm going to start with the i's, because those are like terms. We get 14i. Here, it doesn't look like I can combine these yet. Let's take care of that I first. Negative 10 times negative 1, I squared. And so I get 12 plus 14i plus 10, which ends up giving me a 22 plus 14i as my final answer, another complex number. All right, let's do 2 more. Just kind of rehash. We'll go pretty fast on this one. If you think you're getting it, feel free to try it on your own. Pause the video. Give it an honest try. If not, then feel free to follow along. We got 2 times 1 is 2. 2 times negative 5i would be negative 10i. This would be positive 3i. And that would be negative 15i squared. So I've done the calculations in my head now. Okay, instead of writing them out the pairs, but if you still need to write out the pairs, that's fine. Combining of some like terms, we get negative 7i. I'm going to go ahead and rewrite this one as negative 1. We see that would now be a plus 15 instead of a minus 15, and so we end up with 17 minus 7i as our final answer. All right, this last one here is going to operate the same way, but it's going to kind of be a cool introduction to the next idea. If you remember, these two are considered conjugates of each other. That's a number from way back, or I'm sorry, a vocab word from way back when. Conjugates, meaning they have the exact same pieces, but the sign in the middle is swapped. Here in a multiplication problem, it's just kind of something funny that happens. So we go ahead and multiply. You've got 3 times 3 is 9. 3 times negative 4i would be negative 12i. 4i times 3 would be a positive 12i. And you get a negative 16i squared out of the last two. Now, here's the funny thing that happens. These two end up canceling. But notice we still have an I in there. We have a 9 minus 16. Oh, but wait, that is an I squared. And so we have a negative 1 here. And we get 9 plus 16, which is equal to 25. The unique thing that happens between conjugates is that they not only get rid of variables, they get rid of imaginary parts. They get rid of the imaginary part altogether and go back to being a real number. All right, this idea we're going to piggyback on and go to dividing complex numbers. And here we go. We're going to take the conjugate. So this is very similar to rationalizing. If you want to leave yourself a little note, this is the rationalizing of complex numbers. It is the exact same thing as when we did the rationalizing video. So here I have 29 over 5 plus I. In other words, I have 29 over 5 plus the square root of negative 1, and that's still ugly. We still don't like radicals in our denominators. And so we're going to do the same thing we did before to fix it. Okay, I'm going to go back to the I version because, frankly, I don't like writing square root of negative 1. It's easier to write an I. We're going to multiply by the conjugate. 5 minus I. Same idea. But what I multiply to the bottom, I must multiply to the top. So I'll make sure I do both. What is, careful, don't just cancel them out. 5 times 5 is 25 plus 5i minus 5i and minus I squared. Which cancel there. That's going to be a negative of a negative 1. And so we end up with a 26 on the bottom there. On the top, we get 29 times 5. Don't know that off the top of my head. I know 2 times 5, or 20 times 5 is 100. And 9 times 5 is 45. So I'm going to go ahead and guess 145. Hey, I was right. Minus 29i. Now, was there a huge reason for doing that? Not really. Okay, if you did want to do it, you can. It didn't help us simplify anything. Sometimes leaving it out actually helps you simplify, as we might see in this next part, but at that point, it's really up to you. It's rationalized, though. The I is now in the top. The I has been moved so that they still equal the same thing, but it's in the top. All right, let's do another one. Here we have the same problem. We have something down below that we do not like, so we will multiply by the conjugate. Same binomial, but opposite sign. When we do that, we get 5 times 5 is 25, plus 10i minus 10i, and minus 4i squared. Remember, if there is something in front of that, you also have to multiply those too. It's not just going to be I squared on the back. All right, we've got these canceling. That's 25 minus 4 times negative 1. In other words, we have 25 plus 4, or 29. Lovely. Here we got to multiply by the same thing to the top, though, the exact same thing. And now we're just back to a multiplication problem. So we have 40 from the 8 times 5 minus 16i plus 45i and minus 18i squared. Okay, these two in the middle combine, 45 minus 16, would be 29i. Oops, sorry. Drop the 40. Well, we'll put it here. 29i. And then we've got that 40 and a minus 18 times negative 1, right? Oops, I'm on the edge of the page there. Okay, so what's going to happen there? We've got the 29i still chilling here, but we get plus 40 plus 18. In other words, 58 plus 29i. Now here, we may want to try simplifying this. You notice how 29 goes both into 58 and into itself. And so we can reduce this down to 2 plus I. So we do want to simplify a little bit. And now it's not just a horrible fraction. It's not even a fraction at all. So that's kind of nice. All right. Let's do one last one. Again, we see an I on the bottom. You're like, well, it's just an I. That one's pretty, right? Unfortunately, no. It's still square root, right? At the end of the day, it still says square root under the denominator, or in the denominator, and we don't like that. So how do I get this out? Maybe it might be a little easier to see what to use if we do put it back as a radical. When we do that, we can see if we multiply by another one, we would get a whole negative 1. And that is what we're going to do here. If we multiply by another 1, we get a whole I squared, which is negative 1. Okay, so it works the same way as if it was a radical. But what do I do at the bottom, I have to do the top. So I end up with I squared there plus I. We know I squared is -1, so we get 1 minus. And dividing by -1 just flips the signs, and so we get 1 minus I as our final answer. All right, I went a little fast because, again, we've done most of this with real numbers. These things aren't changing. This is the same stuff over again. And so addition, subtraction, multiplication, division operate the same way. You just have to deal with the I squared, really, at the end of the day. The last thing we're going to talk about is what happens when you take I to the third and the fourth power, and then the fifth power and the sixth power. And I will see you there in the next video to talk about that.